This is me, a 17-year-old who was bored out of his mind, and of course the only logical decision I could come up with was making a mind-controlled game. But how did it come to this? It started off with the release of
the Apple Vision Pro.
This is the Apple Vision Pro.
This is the new Apple Vision Pro.
Apple Vision Pro.
Apple's highly anticipated Vision Pro.
Not the most comfortable headset.
I just didn't really get the vision.
Not perfect for everything though. For typing or complex tasks, you're gonna want things like hands or a keyboard or controllers or eventually a neural interface.
Okay, for those of you who didn't catch that, Mark Zuckerberg just referred to neural interfaces, also known as brain-computer interfaces. This technology allows you to record the electrical signals in your brain that fires when doing activity that can range from deep sleep all the way to physical activity. And when harnessing this data, you can do a lot of cool things. So this is the Muse Headband 2 EEG, a type of brain-computer interface that I'll be using throughout this whole video to record the data I want for my project. Before I start, I just want to say I used the help of a utils file created by a developer in the brain-computer interface space, and it provided a lot of the background work for the functions and methods I use for my program. Now that we have the tech that we need to get our hands dirty, I decided to create a game revolving around training your focus levels. And the reasoning behind this is that the community that is most impacted by this tech are people facing difficulties in motor function capabilities. And a common pattern among this community is cognitive and focus training to maintain a sharp mind and reestablish neural pathways they might have lost. So developing a game in this area and showing how easy it is, I think will be impactful for people to start developing in this area using BCIs, especially integrated with VR. First, I had to do the initialization process for the Muse Headband, so I had to import the libraries I need, such as the NumPy and PyLSL, which lets me handle the EEG data and find the data stream using the function resolve by prop. And also do a 2-second timeout so that if no stream's found, you can raise an error. Then you have to create an inlet. This allows us to pull chunks of EEG data for processing purposes. I made it around 12 samples per chunk of EEG data. Then you have to correct and synchronize the EEG data stream to the local computer time. You can do this by using the inlet time correction function. Now that you finish the initialization process, you can now go on to define your epoching parameters. But what is an epoch? Well, think about an English class. If you're analyzing a book, you're usually going to take out short passages from that book to identify patterns and different types of ways to analyze it easily. Now, same with the signal analysis. Taking epochs is simpler for us to process in our program. The parameters you have to define are the buffer length, shift length, overlap length, and epoch length. Your buffer length is basically the total duration of data that you want to store and update continuously. Your epoch length is the duration of each individual segment or chunk of data that you extract from the buffer for the use of analysis. Your overlap length is basically how much your consecutive epochs overlap, and your shift length is basically the time shift between the start of consecutive epochs. After that, you can create a class called bands. This identifies your delta, theta, alpha, beta waves as different types of bands and associates numbers to them, such as 0, 1, 2, and 3. Then declare your index channel. This refers to the electrode you'll be using from your Muse Headband to stream data from. I'm using the left forehead electrode, which corresponds to number 1. But the right forehead is 2, left ear is 0, and the right ear is 3. Okay, now we'll be looking into the mechanics behind our ball class. The ball class has attributes such as position, velocity, gravity, the attributes that controls the ball's movement in the game. But the function I want to be looking at is the calculate beta metric. This is responsible for processing the EEG data and determining whether the ball should jump or not. It is done by this computing beta metric, which is the ratio of beta band power to theta band power. The beta metric is calculated using the compute band power function, which extracts features from the EEG data. But what exactly are band powers? Band powers represent the power or energy within specific frequency ranges of the EEG signal. In our game, we're interested in 4 main frequency bands: delta, theta, alpha, and beta. Back to the compute band powers function. This function divides the EEG signal into these frequency bands, and then calculates the average power within each band.
It does this by applying the Hamming window, which is a function that reduces the signal leakage in the EEG data, then applies the fast Fourier transform in the NumPy library to convert the data from a time domain to a frequency domain. This gives us a power spectral density of the EEG signal that we get. We then take the average of this power spectral density within these frequency ranges to obtain our band powers. Yeah, this function does that much. Once you compute your band powers, you can go update your data. I store this data in a variable called band buffer. Taking this band buffer, you can go now and smooth it out by taking the mean of all epochs. This meaning your delta, alpha, beta, and theta frequencies are all getting averaged out. Now you can calculate your metric using your beta over your theta, which gives you the metric you'll be using to calculate your focus. I'm not going to go into detail of every class involved in the program, but the rest are just functionalities of normal Pi games, like the main game loop, animations, updating frames, and so on. But to trigger a jump, you'll have to identify a value you would like to set as the threshold from the metric we calculated before. In my case, I figured 3 would be the focus value that triggered the jump. You can then start streaming in your data by this application via Lumuse. You can see my data streaming in on the left. Then you can run your program in PyCharm for me, but whatever platform you use to do your code. And then as the application starts up, you'll see my game pop up, and you can see my beta metric being calculated and displayed on the left corner. And once you hit the threshold, you'll see my ball jump. Now you'll have to focus for the ball to jump, and there are a little bit of discrepancies, but for the most part, I gotta work out for my focus abilities. Thank you for watching, and make sure to subscribe for more videos.
Music